Morning, class. My name is Sayasit Yang Sao. I am your instructor of technology. I am going to present a delta connection with balanced load. This is the delta balanced load, and the power is supplied by this three-phase delta connection source with VL as the line voltage, IA current from the source, IB second current from the source, and IC the third current from the source. Let's assume that VL is equal to 120 volt with 60 Hertz, and let's Z of the delta equal simply a resistance of 12 ohm value. So the current in each phase is equal to 120 divided by 12, which gives 10 ampere. As reference, let's AB equal IP 90 degrees. Let's IAB equal I phase with 90 degree as reference. So it is 10J in rectangular form. IBC equal also to the phase current with an angle of minus 30 degrees. Minus 30 degrees because we have to have an angle between IAB, IBC 120 degrees. Now the value of IBC is equal to 8.66 minus 5J. It is the same for the current phase ICA, that is equal to I phase with an angle of minus 150 degrees. This is because we need between ICA and IBC an angle of 120 degrees. The value of ICA is equal to minus 8.66 minus 5J in rectangular form. Having the current flowing in the phase, now we need to know the current from the source. Okay? First, the current from the source IA is here, is equal to IAB minus ICA is equal to IAB flowing out minus ICA flowing in to the point A here. So, making the difference in complex numbers, IA is equal to 10J minus 8.66 minus 5J. So after subtraction and addition, you get IA equal to 8.66 plus 15J. That is 1732 ampere with 60 degrees. IB in turn is equal to IBC minus IAB. Okay. Now, putting the difference of this IBC and IAB from the value in complex numbers, which are here, you will get 1732 ampere with a minus of 60 degrees. Finally, the line current IC is equal to the phase current ICA minus the phase current IBC. Substitution ICA and IBC by the value, okay, which is minus 8.66 minus 5J minus 8.66 plus 5J here. So the J, okay, cancel. The J are cancelled from here. It remains 8.66 minus 8.66, that is minus 1732, and that is 1732 with an angle of 0 degree for IC. Alright, now let's summarize our problem. You know that in a balanced delta load, the current is, the line current is the square root 3 of the phase current. So it is the square root of 3 multiplied by 10. It gives you 1732. And we just found out IA, IB, IC equal to 1732. So the relation of the line current and the phase current are completely correct here. Last step to understand is the angle between a line current and a phase current. Consider, for example, the angle between the current IA and the current AB. You will get 30 degrees because IA is equal 60, okay, and IB is equal to 90. The difference between the two is exactly 30 degrees. Class, we should also check with the phasor diagram of the currents in a delta balanced load. Here on the vertical line, you can see the current in the phase AB, okay, making 120 degree with AB. You see IBC, and IBC is making with ICB 120 degrees also. Now, the vector that represent the line current IC, IB, IA are clearly indicated in the phasor diagram. The angle between the line current IA and the phase current IAB is 30 degrees. You can also see the angle of 30 degrees between IBC and the line current IC. There is also an angle of 30 degrees between the line current IC and the phase current ICA. Thank you very much for today's class. We'll see each other again next time in another issue of electrical engineering.